I prefer to measure it. It's true that establishing the gradient, the remote potential is very difficult to have the right conditions. That is, that there are no buried pipes, no buried cables, no petroleum gas pipes, no high voltage lines, no power lines. It's difficult to find the available land to make that measurement. That's why I agree with the standard. It's sometimes difficult to determine that remote potential. But let's look at the standard, as I tell you. Let's open the standard. Well, notice one thing. Because corrosion specialists are good at designs. In calculating this, we always focus on this: buried pipes, gas pipes, petroleum, water, pipes that are high impact, or rather that transport products with high calorific value, or indifferently. It could be a water pipe, but if the water pipe is a pipe of a main line that supplies an entire city, imagine if the pipe bursts due to corrosion and we leave an entire city without a supply of drinking water. It would be a sanitary chaos. A chaos. In all aspects. So we always focus on our pipes. Of course, pipes are naturally susceptible to corrosive processes and other factors. This is an image where you can see damage to the covering. Where exactly is it located? We can see the coating damage here, therefore zones will form of both anodic and cathodic. We would have an anodic zone where the pipe is oxidizing, losing metal thickness due to oxidation, and will eventually fail, collapse into massive leaks or product spills. And there is a zone that will receive the protection current where this occurs in these scenarios. Gentlemen, this is the zone where the area that corrodes is presented. Normally we will see it, we enter nuance. For example, let's suppose that here they replaced the pipe because it was damaged in the past and they installed a new pipe. But it happens that the new pipe has more energy. It has greater energetic properties compared to the old one, and the same vicious cycle will always occur. The new one will protect the old one, the old pipe, and again. If no attention is paid to the quality of the covering, the coating, the protective coating, we will always have these corrosive phenomena. So, we, the corrosion specialists, always focus on this, addressing these problems. Now then, we normally install systems of cathodic protection systems to reverse these processes. We always use a rectifier for alternating current and call it the transformer for direct current. It can also be called a current converter. They're a cable that connects directly to the pipeline, and another cable that connects to the ground bed to the anodes. If you see this, these are our years of Catholic protection. These years can be of iron, silicon, magnesium, chromium, zinc, aluminum, MO, X. It can even be scrap, waste metals, up to old pipes. In this case, we see that they are anodes, vertical, and they are connected to a common point, which would be this common point. It would be this point here. That would be the common point with vertical anodes, but we, as corrosion specialists, have to adapt to the terrain conditions. Whether it's because the circuit resistance affects us a lot, the resistivity of the terrain, the resistivity offered by the electrolyte, and that's why we have to make configurations. This is indeed one of the examples, but here we have another example of vertical anodes, but in series, or the famous deep ground beds. Here we manufacture or design ground beds with steroids, if you want to put it that way. Because when we make this configuration, and mind you, sometimes we have to install this system 100 meters deep, 200 meters deep, 300 meters deep, because that's where the resistance was suitable for us. In the calculations and field measurements, it showed us that the resistance at that depth was the most suitable for installing that anode system. Electricians might see it as a ground bed also, because after all, this same configuration is also used in grounding systems in their electrical stations. In Venezuela, electricians call these ono, chemical bars. They call these chemical bars. They are simply anodes, magnesium, zinc, or aluminum, or ferrosilicon chrome. When we, the corrosion specialists, select specialized materials, because our purpose with this is for them to be resistant to current discharges, so that we design for 20, 30 years, and we estimate in our calculations how long that material will last. Based on Faraday's law, we can calculate how much is the loss of metallic thickness that this material will suffer. And based on that, we make our design. That's why you will see that in our designs, the total resistance of this almost never exceeds 1 ohm of resistance. Why? Because we are talking about money. The more resistance it has, the more energy consumption, the more energy the client will have to use to be able to supply the voltage and current we need to protect our pipeline. So basically, that is the purpose, and that is the reason why the total resistance of our ground bed is always in our design. In our calculations, we try to always keep it below 1 ohm. In Venezuela, for example, the electrical code for houses, residential systems, I have seen many videos where they say that the code states that the grounding for a house, the resistance should be 15 ohms or 10 ohms or 5 ohms. Wow. When I see those values, to me that is too high for grounding. That's why we design based on these concepts, these premises. There are other configurations, many configurations, but in this case, gentlemen, we have to resort. This is another configuration. Vertical anodes, but parallel to the pipeline. There are times when the soil resistivity does not allow us, or the availability of the land is not the most suitable, and we have to resort to designs of this type. This is another type of design. They are also vertical, but notice that they are anodes connected to a common point. So we are talking about anodes in parallel, and each string or each line of anodes in this case has 4 anodes for each parallel. So they are mathematical equations. Here, the equations of de posición de Darwin. And mathematical calculations are made to calculate the total resistance of the ground bed. But if you want to see it, gentlemen, that total resistance calculation is mutual resistance calculations. Those mutual resistance calculations consider the separation of the anodes and the distance, this separation here. We take into consideration the separation of one line against another as well, and the entirety of the entire. The distribution or configuration of the years also enters into the mathematical equation. So these are bottom calculations, as I mentioned to you. In this case, Sunde and Darwin equations, which are also applied by electricians and, of course, in their electrical stations. Wow, we are already talking about complex numbers, imaginary numbers. And that type of calculations. So notice that this is a universe, sir. This is a specialization. So this is more or less how the distribution of currents through the electrolyte is. And how do the currents flow through the pipe and the ground bed? Here is how the currents are distributed, or how they travel through the ground. Because in the ground, there is the presence of electrolytes or elements capable of conducting electric current. And here we see the big B that is already wearing out. It's already deteriorating. It's already being destroyed by the action of the air. But we calculate and estimate the useful life of that. The purpose is to protect the pipeline against corrosion. And you can see the electrical circuit in general. This is a sacrificial anode. This that you see here. It's the same thing that electricians also use. What happens is that electricians use copper bars, copper wire, they connect them to houses' electrical panels, but their grounding systems discharge through their copper wire bars and transfer to the bar that is on the pole that supplies the electrical voltage. There the electrical circuit is closed when there is a fault in the electrical panels. In our case, cathodic protection, well, our idea is that this annual sacrifice protects the pipeline against corrosion. This is another configuration of sacrificial anodes, and notice that connected vertically but parallel to the pipeline. And as you can see, gentlemen, a common point. Which is the common point? The common point is this one here. Sorry if I sometimes get tangled up with this. The common point is this one, but then all the other anodes are interconnected. And we have the connected cable. The connected cable that links the pipeline with the group of anodes. So, this is the other type of configuration. Everything is calculated in cathodic protection, or the corrosion specialists. Calculate all of this, gentlemen. This is to give you a general idea that this is a universe. A sacrificial anode, as I showed you earlier. This how one is works and how the currents are distributed in a sacrificial anode. Here you can see it deteriorates, it gets destroyed. We know when it will be destroyed, and the field measurements also indicate to us this one has reached its lifespan, its useful life of operation. But this here, just the same, is used by electricians in their electrical stations. When the resistances are very high, they have to resort to the famous chemical bars, or sacrificial ones. They are more efficient. They discharge the currents with lower resistance to the circuit, and they have a longer useful life. This is the general theory. I hope you understood that. Now, let's look at the Code of Electrical Engineers. Notice that they're code. That's why I tell you, I'm not inventing the wheel. Salt water is in the sea. Why would I invent salt water if they have a procedure for this? Recommended practices for determining. Sorry, this is not the standard I wanted. Sorry, this is not the one I wanted to show you. I think it's this one here. This one here. Why would I invent? I mean, ENIS International tells you how to do it. API, American, Petroleum Institute also tells you, ASME also tells you, ACTIAM also tells you, ISO standards also tell you. But if I'm going to measure resistivity and resistance grounding impedances, who am I going to consult? I will consult the standard of the specialists, the electronic and electrical engineers. And here is the guide for measuring ground resistance, grounding impedances or grounding impedances, and measurement of potentials in grounding systems. They tell me how to do it. They tell me what I should take into account and what the safety measures are. And for example, let's look here in point 7, they tell you how to make the measurements, resistivities. But in the measurement of impedance, remember that when we are going to measure resistivity and impedance, we do not use S-eddy voltages because we are not interested in polarizing the bars or test pins. That's why we use alternating current voltage. Those devices have an internal battery, but they inject the alternating current voltage. So when I go to the grounding part, impedance, because in impedance, when we talk about impedance, AC, voltage resistance, it's because we are already talking about the vector sum of resistance. That's why we talk about impedance. Now then, notice that they tell me this has been applied since the year 1950. I thought I could move it, sorry guys. But I can use it from here. Lightning. I didn't make a mistake. Sorry, I went back. And now, like me, to goodbye. Sorry guys, I went back. I'm not very skilled at handling the table. This okay, here we are. So they tell me that the method for measuring impedances or resistances is not grounding. This they use. They tell you that you can use the 2-point method. So I don't want it to take me out, because I take myself out. The 2-point method is one method, and the 3-point method, 3 measurement points. That is the rod we are, the grounding we are going to evaluate, and 2 pins, where the voltage and current are injected to be evaluated. But normally, they talk to you. Notice that this method let's emphasize this here. This failure method only simply applies what I can highlight. This method is applied in voltage, current magnitudes attenuation in transformers. Voltage transformers and current dividers. That is, this is applied in their electrical stations. But they also make a clarification. Where did I see it? Let me read. Okay. Well, in a certain case, this method is the most used because it is the most reliable, the potential drop method. And it is where they place more emphasis on the application. And the potential drop method consists in as I mentioned, in 3 pins. In 3 pins, this is the test pin, the grounding that we are going to evaluate. This pin is the one that should be remote here, where we are going to inject the current. Here it connects to C2. On this pin, we are going to measure the voltage, and on the measuring equipment here, we connect to P2. And at this point in the grounding that we are evaluating, there is where we are going to connect C1 and P1. So, this is the configuration they mention. Notice that they emphasize on a distance D. This distance D is the one that should be remote. And the PP distance is the one that should be at 62% of the distance of D. Let's see it. Let's see well, I wanted to comment on what I disagree with in this standard. Notice what the standard says here. Let's position here to write, perhaps add a few more words. The typical distance of separation should be 5 times the length of the grounding dimension. This from this, here where the grounding is, right? And they tell me that this distance of, for example, if this grounding has a length of 10 feet, they tell me to multiply by 5. So according to them, they are telling me to place this at 50 feet. That's what they recommend. I do not agree with this. But we will see it in the analysis I did of potential measurements, because remember that I did the potential measurement based on the distance. I graphed it, and I did not present it in Excel to show you the analysis. And in fact, I measured 500 feet because my ground bed in my case. In the field measurement, my ground bed had a length of 100 feet. And I measured the remote potential at 500 feet, and even then I realized after analyzing the data that this was not my true remote potential. We will see the analysis of the information now. But, well, and this is what I do not agree with them on this. This should be measured, because this tends to reject systems. An inspector might say, no, the resistance is too high. You have to improve it, and you are really seeing it wrong. You are doing it wrong. Okay, let's see the manufacturers. Now, I wanted Moon to tell you this. Notice that this graph represents to me the location of the pins. The location of the pines, where we are rehearsing here at 0 distance, would be the ping or grounding that we are evaluating then. And here would be the remote pin. And they tell me these are mathematical calculations that have already been done, gentlemen, so this is not improvised at all. They tell me, notice that here we have pending. Here we have pending. And here we also have pending. But this area has no slope parallel to the x-axis. And they tell me that in this area, notice that the number 60 is here, approximately 62%. They say measure me, you start placing the measurement pin. The potential pin is here. Remember, this is the grounding we are evaluating. This is where the pin that measures the voltage goes. And this is the pin where we inject the current. So they say it measures at 62%. But if you notice, I have a margin. To position myself. I can install it at approximately 52%, which would be here, or at 72%. If I place the pin in this area, it would be in the zone of where there is no slope, and the measurement would be valid. That's what this graph means. Let's look at it with the manufacturer's equipment. But I wanted to explain where the 62% comes from and why. And wait, note, this standard is a global monster. This includes calculations of, here we can see what happens when I am very interesting. What happens when I am very close? Remember that the test pin is this one right here. The large one we are evaluating, the one that measures the voltage, is this one. And the remote pin is this one, which is what this graph tells me, that if this pin is very close to the test point, it will give me lower values. And if this pin is very close to the remote, that is more than 62%, I will have higher readings or higher resistances, and I will reject the test. So here I am giving false information. I am saying it wasn't super good, is very low. No, you gave it to me wrong. What is rejected? The resistance is very high. No, if they put it in this area, then they put it wrong. It's rejecting, but without knowing why. Okay. As I tell you, this graph also shows me what happens when I get closer. Look at it in this way. Here would be the remote pin, here would be the test pin, and here is the potential measurement pin. What happens when I get closer? Very close to the remote pin. Look at all the errors that a measurement can have. And what happens when I get closer to where our test pin or the grounding we are evaluating is? Very low resistance, and I will test it without having the justification. This standard is phenomenal because it not only shows me how to do it, but it also tells me later how it tells me how to analyze and interpret the results.